In this presentation, we're going to look at shear and some different failure mechanisms that can happen when we're talking about shear, and also how we can estimate the strength of these different failure mechanisms. Our learning objectives for this section are to identify the primary types of shear distress occurring in reinforced concrete members. We'll see how we can explain how reinforced concrete members resist shear stresses. Explain and illustrate the three ways that concrete resists shear after cracking. Explain and illustrate the two roles of shear reinforcement in resisting shear. And use ACI 318 and AASHTO LRFD to estimate the shear strength of reinforced concrete members. We're moving on from our discussion looking at axial loads and flexure and to now combined shear and flexure. We're first going to look at different shear mechanisms and how shear affects different members. We'll see how to integrate shear into our design. We'll see an ACI approach and how ACI currently approaches the modeling and estimation of our shear strength, and then also some different truss analogies. We'll look at a classic truss analogy, and modified truss analogy, and a compression field theory. So shear covers a broad range of failure types. And I want to introduce you to several different types of failure that fall under this category of shear. We'll start our discussion on shear by looking at the shear distress that we see in different members. And we'll start with beams. In beams, we have shear distress behavior dependent on the shear span to depth ratio. The shear span is the distance between a point load and the closest support here. So this is our distance A, our shear span, and our depth is just the distance between our extreme compression fiber and our tension steel. We can estimate our shear span with a distributed load based on the ratio of max moment to shear, which we'll look at in some of our example problems later. What we'll see is that if our shear span to depth ratio is between 2 and 6, we'll have kind of a classic shear failure type where our incline cracks are going to be due to a combination of our shear and flexure stresses. If we have an A over D, or shear span to depth ratio, less than or equal to 2 in beams, we'll have what's called deep beam behavior. And this is when we'll need to use strut and tie, the strut and tie method to estimate our strength. There are two main types of failure or classic failures that can happen in our beam members. We can have a web shear failure shown on the left here, and also a flexure shear failure. A web shear failure, essentially we're having a failure within our web, the concrete within our web. So our shear stresses are causing more or less a compression failure of our concrete in our web section. Our flexure shear failure will have flexure cracks that start to turn into shear cracks as the shear stresses increase. Shown here are two videos from some shear testing that I did in some previous research at the University of Texas. So on the left, we have a web shear failure. So we'll see here. You can see crushing of the concrete in the web of the section. The next failure is a flexure shear failure on the right here. And in this section, we had a flexure crack that came up and became a shear crack. These are both pre-stressed sections, so you can see that the shear failure is a little more explosive than would be in a non-pre-stressed section. But you can see in our flexure shear, we have this kind of S crack that happens. And that happens in a pre-stressed member. When we have shear span to depth ratios less than or equal to 2, we're going to have deep beam failures. So these members we need to design and design differently than typical beams. Also in this category, we can have brackets and corbels. So any type of ledged member where we have a load applied on the ledge. And here you can see some strut and tie models to model the stresses going through these beams, where the blue dotted lines are compression and the red lines are tension, making up our truss models with these forces. You can see that failure of any of these sections is either going to be caused by yielding and failure of the steel, so failure of one of these red lines, or crushing of the concrete, so failure of any of these blue dotted lines. Here you can see a failure of a ledged member from some testing done at NC State. So here we have like a punching shear failure of our ledged member. And here we'll have a failure of a reinforced concrete deep beam. So our reinforcement is these external bars here, and we're applying the load from the top. We have supports here at the bottom, and the reinforcement here is engaged with our beam in the back of our back node here. So we'll see our compression element here. So we could see here we had the top corner of our section detached from the rest of our section due to some tension that develops there, and then followed by crushing of our concrete near the location of our support right there. Another type of shear critical element is a shear wall. And the cracking and failure of a shear wall is dependent on its height to width ratio. So the height to width ratio. If we have an H over L less than 2, we have a squat shear wall, and this will behave like a deep beam member. If we have a high rise shear wall, where we have an H over L greater than 2, we'll see flexure shear cracks. So this will behave more like a beam element with typical shear. So you can see here with squat shear walls, they're going to behave like deep beams. So we can create a strut and tie model to model the flow of stresses through the element. And with our high shear wall, we'll have, it's going to behave similar to just a cantilever beam. And here you can see example failures of each with our squat shear wall with this large diagonal crack through, and a high-rise shear wall where we have more flexure cracks that are turning into shear cracks. Another type of element that we can have shear failure in is a column. So columns are either going to perform similar to beams if they have low axial loads, or we can have shear failure triggered by the crushing of our compression core. And this would be if we have high axial loads. So in general with columns, the axial load that's applied on the column is going to impact our shear capacity and shear behavior. So our axial compression is going to increase our shear capacity, and axial tension will decrease our shear capacity. We can also have a different type of shear mechanism in the joint between beams and columns, or beam-column joints. Our beam-column joints are going to develop a diagonal crack in the center, and they're going to fail eventually as a result of diagonal compression of the strut. So we'll have compression forces coming in from our beams and our columns, and beams and columns on the other side, and that'll lead to large compression forces coming down the center of our joint, and the tension in the beam and the column on both sides is going to lead to tension running perpendicular to our compression force here. So what can happen? This can lead to failure of the joint. Also, if there's a reverse of loading, then we can get degradation of the joint. So these joints break down under cyclic loading, which you can see in the picture here on the right. We can also have a shear failure at any joints or geometric discontinuities in members. And at these points, we can have a sliding shear failure where we have the section slide relative to the other section, so a shearing along this plane. This is called either shear friction or horizontal shear if you're in beam members. And it's dependent on the amount of steel crossing the joint, the clamping force, so any external force that's perpendicular to the joint that's clamping the two pieces together, and also the concrete interface surface and the concrete strength will affect the joint strength. Shown here is an example of a horizontal shear failure from some testing that I did at the University of Texas. And what you'll see is we'll see shearing right along this interface between our large bottom flange in this bulb T section and the narrow web. The bottom flange is it has a lot of pre-stressing reinforcement, so there's a large amount of force from our bottom flange that needs to be transferred in the web, which puts a lot of shear stress on this interface between the bottom flange and the web. So we can see that the top part of the beam, so in the web and above, shifts to the left, and the bottom part, the bottom flange, shifts to the right as we have a shear failure right along that interface plane. We can also have shear distress happen in slabs and footings. These members are either going to behave similar to beams and exhibit failure in one direction or one-way shear, just like beams or low axial columns, or they're going to fail in what's called two-way shear or punching shear and moment transfer. With punching shear, we'll get this diagonal cone that happens around our column, kind of all the way around the column here. And the slab is essentially going to punch down relative to this concrete surrounding the column. So this is called a punching shear failure. And here you can see some examples of our punching shear failures. So here our column with the cone of concrete surrounding the top and the slab punched through. Here the same thing, the concrete surrounding our column and the rest of the slab punched through. And here you can see that diagonal cone from some research or some research testing, experimental testing. On the next couple slides, we're going to walk through the basic mechanisms of how shear stresses are going to affect the behavior of our beams. So first, in a beam, when we have a combination of moment and shear, we're going to have a combination of bending stresses and shear stresses. We can combine these axial stresses from our bending moments and our shear stresses into principal axis stresses. So we have our axial stresses and our shear stresses, and we can rotate our element to get a diagram with our principal stresses. We can then plot these tensile and compressive stresses throughout the beam to give us what's called a principal stress trajectory. So shown here is a diagram with our principal stress trajectories for both tension and compression. Our compression are the dotted lines and our tension are the solid lines. And we can see that in this diagram, we'll have cracking when any of our principal tension stresses exceeds the cracking strength of our concrete. We can also remember from our discussion on biaxially loaded concrete that when we introduce tension, we're going to dramatically decrease our compressive strength. So in shear, we're introducing transverse tension. So you can see as we introduce some tension in region V, we're going to decrease the compression strength of our concrete. So again, here we're introducing transverse tension, which will decrease our compression strength of our concrete F2. Next, we're going to talk about the basic shear transfer mechanisms. So there are a few main shear transfer mechanisms, which we'll cover on the next slides. The first main shear transfer mechanism is just our concrete shear stress. For uncracked sections, the shear is going to be carried by the tensile strength of the concrete itself. So until our F1 exceeds Ft, the tensile strength of the concrete is going to help to carry the shear. After cracking of the concrete and shear, there are two components related to concrete shear stress. There will be some shear stresses carried by the uncracked concrete in the compression zone, so labeled VCC here, so the uncracked compression zone here. There are also some residual tensile stresses carried by the cracked concrete, labeled V sub CR here. As cracks develop, we're going to start having some interface shear transfer. So our section's going to want to slide along the crack, but we're going to have a couple components that are going to resist that sliding. First, we'll have aggregate interlock. So the aggregate, the roughness of the aggregate on each side is going to create some friction that will resist the sliding. We'll have a shear friction component, which will be again a function of our surface roughness, and then also dowel action. So our steel that's crossing this interface plane is going to resist shear. So our concrete is going to be in compression right here next to the steel, and compression right here. So we're going to, or that steel crossing the plane is going to resist shear transfer. So it's just like if you're holding a pen in between two hands and you try to move your two hands or shear your two hands, that pen that you're holding is going to resist the shearing of your hands, and that's what dowel action is. In deeper sections, in deep beam sections, we're going to have our force transferred directly from our load to our support. And this will behave more like what's called arch action. So here our load is transferred directly to our support. So this is arch action. The final main transfer mechanism is any transverse steel reinforcement that's crossing our crack. So after cracking, our steel crossing the crack is going to take additional tensile stresses developed from shear. So any reinforcement that's crossing our crack, VS, is going to resist shear directly. We will next walk through a quick derivation of the ACI 318-14 detailed method. For this derivation, we will look at an element right above a crack in our section with a certain state of stress as shown. This element has some tensile stress and also has some shear stress. We can rotate this element to find the maximum tensile stress that's going to be in the element, so our F max. We also know from our shear stress expression that our shear stress is going to be equal to just VQ over IT. Our Q over IT is just going to be some constant K1 divided by BD times Vn. And we're doing that to get it into the form that we need for our derivation. We can also estimate our tensile stress from our flexure, where our stress is proportional to our moment divided by AS times D. just from our nominal moment expression, where we have, we're summing our moments about the centroid of our compression block. So we can transform this steel stress to concrete stress by taking it times EC over ES. If we plug in some of these values into our FT expression, then we'll get our FT is proportional to MN over BD squared times the square root of F prime C over rho reinforcement ratio times ES. And we can simplify that further. We can, again, remember our F sub V, our shear stress from the last slide, and then also say that our F max is limited to some K times our square root of F prime C. So this would be the tensile strength of our concrete itself. We can substitute all those variables from the previous slide into our maximum shear expression, maximum stress expression from 2 slides ago, and we'll get this expression here. And then we can solve for Vn over Bd times square root of F prime C, and we'll have this expression here. Within this expression, we'll define an independent variable, x, and a dependent variable, y. And substituting in the independent variable and dependent variable into our previous expression will give us this equation here. So this expression is the kind of theoretically correct expression for this derivation based on our starting stresses that we're looking at. And we can calibrate our different constants, our different K constants, using experimental results. So researchers saw that the results from the equation shown on the previous slide were similar to results from just this linear expression where we have y equal to a times x plus b. And this is the simplification that ACI uses. So then we can calibrate this equation with our independent and dependent variables to give us this equation shown here, which is the equation that we find in ACI 318.14. And we can see on this slide how that detailed expression lines up with our experimental data. So the detailed expression here is this dotted line with all of our experimental data. And we can also see where our 2 square root F prime C lines up with the experimental data. So this is the simplified shear expression for non-pre-stressed sections. So in ACI 318.14, we have a simplified and a detailed expression for non-pre-stressed members without axial force. Our simplified expression is just 2 times lambda, which takes into account the effects of lightweight concrete, times square root F prime C, where our units here are PSI, times BW, the web width, times D. And our detailed expression also takes into account the effect of our reinforcement ratio and our shear and moment at the section that we're looking at. A new one-way shear provision was developed and implemented into ACI 318.19. 4 considerations were highlighted in the development. The first consideration shown on this slide and takes into account the influence of the percentage of longitudinal tension reinforcement, or rho W, moment, or longitudinal strain in the tension reinforcement, epsilon sub s. In general, there isn't any consensus on how these factors influence shear, but rho W is directly related to M sub U, so our ultimate moment, and the depth of the compression block C. So approaches that are based on aggregate interlock and the depth of the compression block both agree that our shear stress is proportional to this rho W to the 1/3 power. So this component made it into ACI 318.19. The second consideration is the influence of axial load and pre-stressing. There's a general consensus that axial load and pre-stressing both impact the shear resistance, but the previous ACI 31814 had 5 different equations that included the impact of axial load and separate equations for pre-stress concrete. So some codes account for the effect of axial load and pre-stressing through longitudinal strain and have one equation for the shear resistance of our concrete. So these factors were considered in the development of ACI 31819. The third factor taken into account when creating ACI 31819 provisions for shear was whether to do a 45-degree or variable angle truss model. So ACI 318 has always used a 45-degree truss model, but axial load and other factors have been shown to influence the actual angle. So AASHTO currently uses an equation based on the modified compression field theory, which is a variable angle truss model. So the angle of our cracking, the angle of our shear transfer depends on the tensile strain in our longitudinal steel, or in the concrete at the center of the longitudinal steel. So this was taken into consideration when developing ACI 31819 as well. The final factor taken into account when developing ACI 31819 was the number of different shear design equations and methods. ACI 31814 had 8 different one-way shear design relationships for evaluating VC and 1 different relationship for VS. So the goal was to simplify and decrease the number of equations for calculating shear. The performance of the new procedures was evaluated based on several databases developed by an ACI 445 subcommittee. So you can see here the statistics for the past ACI 31814 equations and the new ACI 31819 for beams without and with axial compression and without and with minimum shear reinforcement. So note in this table that values less than 1 are conservative when we're looking at the mean. So you can see here how the new equation performs compared to the old equations. More details on this can be found in the paper that's cited here. The concrete contribution of our shear design, our V sub C, for non-pre-stressed members can be calculated using the equations found in this table. So if you have minimum shear reinforcement, then you can calculate VC using either of these 2 equations in A or B, or A or B. If you don't have minimum shear reinforcement, then you need to use the equation here shown in C. And note that in these equations, N sub U is our axial load, our applied axial load, and it's positive for compression and negative for tension. And also note that VC shall not be taken less than 0. So if you have axial tension, that'll decrease the effectiveness of our concrete to resist shear, but you shouldn't take VC to be equal or less than 0. 2 additional limits for our concrete contribution are shown on this slide. The first here is an upper limit on our VC. You can see here that our VC needs to be less than or equal to 5 times lambda times the square root of F prime C times BWD. The other limit here is the limit that our axial load, our compression axial load can improve our concrete shear contribution. So here we have an upper limit, so added axial compression will only increase our concrete shear contribution so much, up to this limit 0.05 times F prime C. The other factor that I wanted to highlight is the size effect modification factor, this lambda sub S. The size effect factor is only used when we do not have minimum shear reinforcement. Shear reinforcement has been shown to eliminate the size effect that happens with shear. But when our shear reinforcement isn't there, we can see that an increased size will decrease our strength. So this size effect factor will take into account that effect. After we form a shear crack, the concrete will resist shear with the components highlighted on this slide. First, we have aggregate interlock that happens along the crack. Next, we have the shear strength that's provided by the uncracked concrete in the compression block region right here. Then we also have some residual tensile stress in the concrete along the crack, so highlighted here by V sub CR. And then finally, we'll have the dowel action that's provided by the primary tension reinforcement. So here's our primary tension reinforcement, so our dowel action will be right there. So for simplicity, we will assume that the summation of these components is less than the original VC that we found using the previous equation. So here are V sub CC plus V sub D plus V sub CA plus V sub CR. We're going to assume that these four components are greater than our original V sub C, which allows us to use the equation that we had on the previous couple slides. These components are only greater than or equal to our original VC if we have minimum reinforcement crossing the crack. So this minimum reinforcement helps to hold the crack together, which allows these four components to engage. If we didn't have minimum shear reinforcement, then we wouldn't be able to make this assumption here. So the first way steel contributes, or shear reinforcement contributes to our overall shear strength is by helping the concrete to contribute to shear after cracking occurs. The second way that steel contributes is by directly resisting our shear. Steel crossing a shear crack, so all of these stirrups crossing the crack are going to directly resist our shear. So we can find our shear stress by taking the area of a stirrup times Fy, the yield strength of the stirrup, times N, the number of stirrups that are crossing a crack. We can approximate our N equal to Z, the length of the crack, divided by S, our stirrup spacing. And with ACI, we assume that we have a 45-degree crack. So we approximate Z about equal to D, the depth of our tension steel from our compression face to our centroid of the tension steel. So then our N is just equal to D over S. So then plugging in our N our expression for the number of stirrups that are crossing our crack into our VS expression, we can get the expression that's found in ACI. So where our VS is equal to AV Fy times D divided by S. And note that our shear crack needs to happen before our shear reinforcement is really engaged in resisting our shear. So before the crack, the concrete is the main thing that's resisting our shear stresses. There's a limit to how much our steel can contribute to the shear strength of our section or our beam or member, because we'll have crushing of the concrete that's going to happen at some point. So with ACI, we can estimate our shear stresses with a simple truss analogy to represent how our stresses flow through our structure. Here where our blue dotted lines are compression and our red lines are tension. So you can see that at some load, the concrete's going to crush under compression. So at this point, when we have failure of this blue element, it doesn't matter if we add more reinforcement to resist these tension stresses that develop, because we already have failure of this blue element that's going to control the capacity of our section. So here, ACI takes this into account by setting a limit on the amount that our steel can contribute to the shear strength of our section. So the ACI, the current ACI limit is that our VS needs to be less than or equal to 8 times the square root of F prime C times BW times D. So this will limit the amount that our shear reinforcement can contribute to the overall shear strength of our section. And again, it's because of crushing that will control the capacity at some point. We also need to make sure that there's some steel crossing the crack. our shear reinforcement is only going to be effective if it's crossing the shear crack. So here on the left, we have some shear reinforcement crossing our shear crack. So our steel is going to provide some shear restraint. On the right, if our spacing's wide enough, we can get a shear crack in between our stirrups. In this case, we have no steel crossing the shear crack, so we're not going to get any shear strength from our stirrups. So we need to ensure that our steel crosses the cracks, and we do that by having a maximum spacing requirement for our shear reinforcement. We also need to make sure that the area of the shear reinforcement crossing the shear crack is sufficient to restrain the cracking and engage the 4 concrete components that we discussed a few slides ago. Here, the figure on the left has sufficient steel crossing the crack to hold the crack together to be able to engage the aggregate interlock and the residual tensile strength components that we discussed before. Here on the right, insufficient steel area crossing the crack is going to lead to large cracking, which leads to a breakdown of the shear strength after cracking occurs. So we need to make sure that we have the minimum shear reinforcement requirement met so that we can hold the crack together and engage our post-cracking concrete shear contributions. With the minimum steel and maximum spacing requirements in mind, we can now design the shear reinforcement based on the shear demand V sub U on the beam. So if our shear demand is less than phi times our lambda times square root of F prime C BWD, then we don't need transverse steel. So it's not required for shear, but it still should be provided for beams to make sure that we have some post-cracking strength. If our V sub U is between this limit and phi times VC, then we only need the minimum transverse steel. So we need to provide our minimum steel requirements, so meet our minimum steel and our maximum spacing requirements, as shown here. If at least the minimum transverse reinforcement is required, then the maximum spacing requirements shown on this slide must be met. The maximum spacing depends on the amount of shear reinforcement required. So it depends on whether our VS is less than or greater than 4 times the square root of F prime C times BWD. And it also depends on whether we have non-pre-stressed or pre-stressed beams. Spacing limits are provided along the length of the beam and along the width of the beam. All beams you'll need to check along the length. Along the width, we'll only control for wider beams, for example, slab beams. And you can see that when we have a larger amount of shear reinforcement required, we'll have a tighter spacing required. If the ultimate shear demand exceeds the factored concrete shear contribution, then you need to design your transverse steel for strength. Typically what you'll do is you'll choose a number 3 or number 4 bars to start. You'll typically have 2 stirrups in your web, so your area of your shear reinforcement will be 2 times the area of your single bar. And then you can choose your spacing based on this equation here, the spacing requirement based on strength, and also the maximum spacing requirements that we saw on the previous slides. So what you'll do is you'll figure out your maximum spacing from strength and from ACI requirements. You'll round your spacing down to the nearest ½ inch, and that's the shear reinforcement that you'll provide along the length. Typically you can choose 1 or 2 spacings along the length, but you don't want to do more than that because you want to make sure that your beam is constructible. After you choose your spacing and you have your bar size, then you need to go back through and make sure that your actual capacity is greater than your actual demand. So phi Vn greater than Vu. And you also need to check your V sub S limit. So you need to make sure that your Vs is less than your 8 times square root of F prime C BWD limit. If your Vs is greater than your limit, then you need to change your design. So you either need to increase your F prime C, increase your web width, or increase your section depth. Typically, you'll want to do one of these first two before increasing your depth. We'll next move on from our ACI 318 discussion to a discussion on how AASHTO LRFD accounts for our shear resistance. The essential difference is related with our truss analogy. With ACI 318, our theta, or the angle between our inclined members with the horizontal, is assumed to be 45 degrees. With AASHTO, our theta is going to be calculated based on the strain state in the member, which is affected by the compression field of the stresses that are flowing through the member. So with AASHTO, we'll calculate the strain at the centroid of our tension steel, and we'll use that to find our theta and also a beta factor, which accounts for the effectiveness of the concrete to resist shear. AASHTO uses methodology from the modified compression field theory. And the modified compression field theory looks at how strain in the section is affected by both flexure and shear stresses. Researchers at the University of Toronto tested a number of these square rectangular specimens under a number of different stress conditions. So we had they had these square concrete specimens with hydraulic jacks on all sides that could apply any combination of stresses. And they looked at how these different combination of stresses affected the strength of the concrete. And they calibrated the modified compression field theory using the results from all this testing. On the next few slides, we're going to walk through how to use the AASHTO LRFD bridge design specification procedure for calculating shear strength. The first thing to highlight is the critical section. So the critical section for shear shall be taken as a distance from dV away from the face of the support. And this critical section is the point where we find the maximum shear demand. So here, the maximum shear demand that we would use in our design, we would find it at this location right here. And you can see here, we don't have any point loads that are located within dV here. So we have the point load out there. If we do have a point load located within dV of the face of our support, then our critical section moves to the edge of our support. So in this case, where we have a point load inside dV, our critical section would be along this plane at the edge of the support. So we would find the maximum shear for our design right here at this point at the edge of the support. Our nominal shear resistance is the minimum of the two equations shown here. So VC plus VS plus VP, or 0.25 times F prime C times BV dV plus V sub P. You can see here the second component is similar to the ACI 318 limit that limits the steel contribution to our shear strength based on the crushing of our concrete at the support nodes. So the second component limits the crushing of our concrete here in that support node. You can see that VC here depends on this beta factor, where beta tells us how effective the concrete is at resisting shear. And our VS looks similar to our ACI equation, except we now have this theta, where theta tells us what this crack angle is. So it helps us to determine how many stirrups are crossing each crack. We also have a V sub P component, which is the vertical pre-stressing component from our pre-stressing force. So we'll only have this V sub P component if we have harped pre-stressing tendons. I also want to highlight that in AASHTO, we need to remember that we're using our units are KSI. So in ACI, our units are PSI, and in AASHTO, all of our units will be in KSI. So we just need to remember that we need to use KSI under our square root here. dV is the shear depth that we use in our shear strength equations. So it's the effective shear depth taken as the distance measured perpendicular to the neutral axis. So here's our neutral axis, perpendicular to that is in this direction, between the resultant tension and compression forces due to flexure. So you can see our dV is this distance here. It need not be taken less than the greater of 0.9 dE. This distance, so dE is the distance from the top to the centroid of our total tension steel a non-pre-stress and pre-stress reinforcement together, and H is the overall height of our section. So typically you're going to find dV, you're going to do your shear design after doing your flexure design. So typically you'll already have your nominal moment capacity and you'll have the amount of tension steel that you have, so tension pre-stressing and non-pre-stress reinforcement. So then you can find dV using the equation here to the right. If you haven't yet found MN, like sometimes in examples in this class, then you can just base your dV on these two limits, so 0.9 dE and 0.72 H. And if you don't know anything about your tension steel, then you can just use this limit based on the height. So your dV you can use equal to 0.72 H. So depending on where you are in the design, you can use these different equations to find dV. AASHTO also has minimum area and maximum spacing requirements. So similar to ACI, these are dependent on the strength of the concrete, our B sub V, which is our width of our web, spacing of our stirrups, and Fy, the yield strength of the stirrups. And then our spacing max is dependent on the shear stress in our beam. So both limits are similar to ACI. When finding the shear strength of a non-pre-stressed member, we can use a simplified approach. And the simplified approach allows us to estimate our beta as just equal to 2 and our theta as equal to 45. And this would give us similar results to ACI. For other members, we can use the detailed approach. So with the detailed approach, the first thing that we need to do is we need to find the strain at the centroid of our tension steel. So this strain will be affected by our moment, our axial loads, our shear in the section, and any pre-stressing that's happened. And it'll be resisted by the stiffness and area of our steel and the stiffness and area of our pre-stressing. If our strain is in, AASHTO uses positive for tension. So if our epsilon S is positive, then we know our section's in tension. If we have a negative strain here, then our concrete is also going to contribute to the stiffness. So we'll have an EC times A sub CT that's going to contribute to the stiffness of our section here, and we'll change the strain in our steel. The area of concrete on the flexural tension side of the member is shown on this slide. The flexural tension side of the member is located below the mid-height of the member. So here, below H over 2. And the area is all this area of our concrete below H over 2. We can easily find this area using a drafting software, or we can approximate the area just based on a scale drawing of the section. Also, we have our A sub PS and our AS, and that's the area of our pre-stressing and the area of our steel, both also on the flexural tension side of the member. So in these equations, we don't consider any steel that's above the mid-height of the member. If we have a section without minimum shear reinforcement, then our next step is to find our crack spacing. And we find our crack spacing based on dV, or the maximum distance between layers of longitudinal crack control reinforcement. So crack control reinforcement running up the sides of our member. And then also based on the aggregate or maximum aggregate size. So we can use these two values to calculate our crack spacing and make sure that we're within our lower and upper limits of 12 and 80 inches here. Next, we can use our epsilon sub s, the strain at the level of our tension steel, to calculate our theta, our crack angle. And we can also use it to calculate our beta. If our section has minimum steel, then we'll use this expression to find beta based on just epsilon s. If our section doesn't have minimum steel, then we need to use this expression, which includes both epsilon s and our crack spacing x or s sub xe component. Then we use our beta and our theta to find our vc and v sub s components. In this example problem, we will calculate the shear capacity of a section without shear reinforcement using the ACI 318-14 simplified method, the ACI 318-14 detailed procedure, the ACI 318-19 procedure, and finally the AASHTO LRFD general procedure. We can see we have this rectangular cross section with number 11 bars in the bottom and top of the section, and we can see we have a simply supported beam with a distributed load. So I'm going to play the failure video now from testing. So you can see here the test setup is inverted from what you see on the screen. So we have a distributed load being applied with an airbag on the bottom, and we have our supports on the top right here and right here. You can see already the flexure cracks developing along the length of the beam, and we'll see a shear crack develop right here on the right side of the beam. So here's failure, and you can see as soon as the shear crack develops, the beam fails. The longitudinal reinforcement helps to hold the beam together to a certain extent, but the beam ultimately fails. And we'll see a slow motion of failure next. So as soon as the crack develops, the beam fails, and you can see the cracking develop at the location of our longitudinal reinforcement, which helps hold the crack together until we have another crack develop and full failure of the beam. So at this point, you can pause this video and go to the other video looking at going through this example problem. For our next example, we're going to calculate the shear capacity of a pre-stressed beam using our ACI simplified procedure, an ACI detailed procedure, and our AASHTO LRFD general procedure. You can see the properties for our section shown on this slide. We have harped strands in this example, so we're going to have different section properties at the end of our beam versus at midspan. Here you can see along the length elevation of the section, so you can see the location of our depressed strands, the center of gravity of our straight strands, and the location of our shear reinforcement. So we have 6-inch shear reinforcement along the whole length and a denser spacing at the ends to handle all of the stresses from pre-stressing. We also have our material properties for our shear reinforcement and pre-stressing strands. So this example goes along with the two failures that we saw earlier. So this is the beam that had a flexure shear failure and a web crushing failure from the videos up front. So at this point, you can pause this presentation and go to example problem 2. There are two additional types of failures that I mentioned up front, but that are considered non-traditional shear failures. The first is called shear friction. And with a shear friction failure, it normally happens at either a cold joint or at narrow shear planes within your cross section. And it's made up of or the resistance or the strength is made up of a clamping or friction force along the cracking plane, and also the dowel action of any reinforcement that's crossing this plane. The other non-traditional shear failure is called shear induced by development failure. It has a couple other names, but that's what we'll call it. And essentially with this failure, looking at our free body diagram that we've been using for shear, we count on the tension reinforcement or this tension force from our tension reinforcement. If we don't have a sufficient development length to develop that tension reinforcement, then our reinforcement is going to pull out of our section, triggering shear failure. So we need to make sure that we have sufficient development length of this tension reinforcement to prevent shear failure. And finally, here's a list of several resources for additional study on this topic.